In the previous lecture, we have discussed the characterization of LTI system with respect to Laplace transform. We have also discussed the causality and the stability of the system with respect to Laplace transform. And the previous section we have discussed the all Laplace transform, which is the bilateral Laplace transform. And in today's topic, we are going to discuss about the unilateral Laplace transform. As the name suggests, bilateral Laplace transform and unilateral Laplace transform. Bilateral means both sided. It means the system is defined for, or the transform is defined for the both sided, means minus towards the minus infinite and to the right infinite or positive infinite. But in the unilateral Laplace transform, it is only defined for the one sided, which is the positive side, which is the positive infinite section. Okay. Therefore, as we discussed in the bilateral Laplace transform, this integral is limited for minus infinite to infinite. The same Laplace transform is happen, but the integral limited from 0 to infinite. It is not defined for the any minus infinite time. It is just for the 0 to infinite. The minus term is indicating here 0 negative or 0 positive. It represents the initial value of a signal. Initial value of the signal is look like a capacitor. If we integrate that, if we use that, then capacitor may be charged or maybe not charged. This charging or not charging represent the initial case of the system. Okay. Therefore, the unilateral Laplace transform have the unique inverse Laplace transform. It means in the bilateral Laplace transform, we have seen that the many signal have the same Laplace transform. Therefore, we take the ROC of the system so that the uniqueness of this transform will remain. But as in the unilateral Laplace transform, this Laplace transform from any signal is unique. Therefore, it does not require any ROC of the system. And it is we have discussed some with example. If we consider ut and minus u minus t, we have seen that in bilateral Laplace transform that both the signal have same Laplace transform, but difference that in left-sided it ROC sigma is greater than in right-sided sigma is greater than 0 ROC, and in left-sided sigma is less than 0. This is the ROC in the bilateral. But in the case of unilateral, as we know that unilateral is defined for the right-sided signal, it does not define the left-sided signal. Therefore, the Laplace transform of this ut is same as it is 1 upon s, and it does not require sigma. And when we dealing with the reverse signal or the left-sided signal, which is minus u minus t, as the unilateral Laplace transform does not define for this type of signal, therefore this Laplace transform of this signal become 0. Okay, let's find some another example. Look that we have to find the bilateral and unilateral Laplace transform of these two signal, and bilateral Laplace unilateral Laplace transform of this signal. Okay, and when we find, for differentiate, we will divide into two part. Okay, have to transform this function ut and u minus t. As we know that the ut have the same Laplace transform 1 upon s, and minus t, u minus t have the Laplace transform minus 1 upon s. And as it is right-sided, then the sigma is greater than 0, and as it is left-sided, then sigma is less than 0. There is no any common ROC, because one equation tells that the ROC is right-sided, and one equation tells that the ROC is left-sided, and in between there is no any common ROC. Therefore, the Laplace transform of this signal does not define. And for the unilateral Laplace transform, it is defined for only for the right sided signal. It is not defined for the left sided. Therefore, the only Laplace transform of ut is defined, which is 1 upon s, and the Laplace transform is 1 upon s, and as it is unique, therefore ROC did not required here. Okay, let's move to next question. Next question is find the Laplace transform of bilateral Laplace transform e to the power minus a mod of t. As we know that the mod of t, I have already discussed that its value is minus t for t less than 0 and for positive t when t is it is positive t when t is greater than or equal to 0. Okay, therefore define accordingly. It represent also like that e to the power minus at ut and e to the power at u minus t. And we have noticed that one signal, which is first signal, is right sided and second signal is left sided. Okay, find Laplace transform accordingly, and the ROC is for the first signal sigma is greater than minus a and sigma is less than a. And when we take a common, because when we define in S plane, one represent the sigma is greater than minus a, it means the right sided, and second define the sigma is less than, means this side, sigma is less than a, it means this side, and then common ROC is between this. It means the sigma should be greater than minus a and less than a. Okay, therefore the common ROC is this, and their combination add this, and this become the minus 2a divided by s square minus a square. But in case of the unilateral Laplace transform, when we consider it, okay, this Laplace transform does not define for this, and it becomes 0. As it is defined for this signal, it is also the same, and it is 1 upon s plus a. Therefore, the bilateral Laplace transform of e to the power minus a mod of t is 2a upon s square minus a square, and the same signal have the unilateral Laplace transform is 1 upon s plus a. Okay, again the next question. The next question is define unilateral Laplace transform for e to the power minus 2t u t plus 2 t plus 1. Okay, let's put it. And as we know that the unilateral Laplace transform is defined for the minus u to infinite, 0 to infinite. Okay, we just put it. It defines the limit of the system. When we put it, it is minus. It is defined for. It look like this, minus 1. But unilateral Laplace transform is defined for the when t is greater than and equal to 0. It is not defined for the minus 1. Therefore, the limit does not change, and it remains to 0 to infinite. Just put it and solve it accordingly. Then we get 1 upon s plus 2. Okay. Then property of unilateral Laplace transform. The first property is linearity property, as we discussed in the bilateral Laplace transform. When if the Laplace transform x1t is x1x and x2x is x2s, then when we combine and apply to the system, then again ax1s is Laplace transform of ax1t plus a bx2t is nothing but the ax1s plus bx2s. Same time scaling, same as a bilateral. If we time scaling, if the t is scaled with at, then their Laplace transform is just 1 minute. From this to this, if t is replaced with at, then here also s is replaced with s divided by a and multiply with 1 upon a. And in the bilateral Laplace transform, this 1 upon a is same for the minus or positive. Therefore, the at the bilateral transform, it is 1 upon mod of a. Okay. Next property is shifting in time S domain. When we shift in S domain, then it is just multiply e to the power s, not t. We note one point that if this is the minus between this, then here is a positive, and if there is a positive, then there is negative. When we next property conjugation, and if we take input to the conjugate, then output s is also conjugate, and the overall after that we will take overall conjugation. Next property differentiation. If we differentiate this term, then in bilateral Laplace transform there is minus, but in unilateral Laplace transform it is just multiply with t. It means when the signal it is also known as the multiplication of time t with st, and it is one time differentiation. If we differentiate with t time, n time, and xt, then their overall value become n time differentiation dx sx. Okay. Next property of convolution. If we x1 have the x1s and x2t has Laplace transform x2s, when we convolve in time domain, then Laplace transform domain it is multiply, frequency domain it is multiply, and reverse is also possible. If we multiply the input, then the output is or the Laplace transform is just conjugate divided by 1 upon 2 pi j. Next property integrate. When we integrate in frequency domain, just t divide by t in time domain, and same as a in time shifting. If if delayed input is applied, then the Laplace transform only multiply with e to the power minus st. If minus there, the same keep the same sign and minus t. In frequency domain we have take the reverse sign, but in the free time domain we take the same sign. Okay. Next property differentiation property. It is the most important property of this unilateral Laplace transform is that if we take one time differentiation in xt, then sx Laplace transform, or then minus initial value of input, and if we take two time, then s square minus s input minus one time differentiation input initial value of x. Okay. Accordingly 3 time, 4 time, 5 time. When similarly integrate, when we integrate this signal, then again it's just divided by s, and also initial value is also divided by integration from minus infinite to near x tau is also divided by s. So next property is most important also, initial value theorem. And in this initial value theorem, if initial value means the starting value, it means that at value at t tends to 0. But as t tends to 0 in time domain, we know that the frequency is reciprocal to the time t. Therefore, the frequency domain s tends to infinite. Okay. Then initial value is just Laplace transform multiply with the signal with the frequency s, and we take limit to the tends to 0. Similarly, in final value theorem, final value theorem means the t tends to infinite, and as we put t tends to infinite in time domain, then s tends to 0 in frequency domain, and similarly s is multiplied with the Laplace transform as in case of the initial value. Okay, this is our last topic. We will discuss some problem based on this. Thank you.